Now in this session, we will discuss certain more examples for the design of PDA. Our first example in this session is the language L is of the form a to the power n, b to the power 2n, where n is greater than or equal to 1. Simply this language says that some number of a's will come, and then after it some number of b's will come, and the number of b's will be exactly the twice of the number of a's. So this is our language for which we have to write our PDA. First of all, we have to discuss its strategy, how we will be, what strategy we will be making for writing the transitions of this PDA. Obviously, because we have to match the number of A's with the number of B's in some manner. So first of all, we must remember how many A's has come. So whenever A's will come, we will push all the A's. So all the A's will be pushed over the push down store. Now, when B's will come, we will start matching these with A's. Now we have to see the relationship. Corresponding to each pair of B's, we have to remove one A. Means corresponding to each two B's, we have to remove one A. This should be our strategy. So key to the success in this particular PDA will be to ensure that corresponding to every second B, we remove an A. And corresponding to the first B in its pair, we should not remove the A. So this we have to maintain, this we have to ensure. Now I am writing its solution. So we will start with the initial situation, that is delta Q0. We will be getting an A in the input as the first letter, and then Z0 will be on the top of the push down store. So first A we are getting, so we will be pushing it. Okay. So as we are pushing, so Q0, A, Z0. As we are changing the status of the PDS, so that's why we are not changing the state. So in this manner, we have pushed our first A. Now to push subsequent A's, we will write the transition Q0A, A, because now A will be on the top of the push down store, and in the input we are getting A. So we will be writing it Q0A, A. So through these two transitions, we will be pushing all our A's. So when all A's are pushed, we are in the state Q0, then we will start getting B's, and we have to match A's corresponding to the B's. So delta Q0, in the input we have received a B, so that is the first B that we are getting, and on the top of the push down store will be an A. Okay. So what we have to do, corresponding to this B, whether we have to remove this A or not, because it is the first B in its pair. So we don't have to remove A. Okay, so that's why we have to maintain the status of the push down store. So we will remember that first B has come. We have to remember this because we are not changing the status of the stack. So we have to change the state. So that's why we are changing the state, suppose say to the Q1. Okay, and then we are writing A. Because we have to maintain the status of the push down store, we don't have to remove from the PDS. So that's why we are writing A. So in this manner, the status of PDS will be maintained and we will be in the state Q1. So being in the state Q1 means that our first B has come. Now, if the second B is coming, corresponding to that B, we have to remove an A. So that is delta. In the Q1 state, we will be getting the second B. So whenever we are in the state Q1, we will be reading the second B in its pair. Okay. So at the top of the push down store is A. Now this time we have to remove it. Okay. So we will be removing by writing null. So we will be removing by writing null. Now question is, to what state we should move? Whether we should again move to Q0. If we will move again to the Q0, and suppose in our string we start getting A. Suppose we are testing a string which is not actually the string in the language. We start getting A. So again we will be pushing those A's. Okay. So that should not happen. So that's why we cannot return back to the state Q0, because first B we were getting in the state Q0. So when next pair is coming, we cannot move back to the state Q0. So we have to move to some other state. So let us say, suppose state Q2 we have moved. So now we are in the state Q2. So in the Q2 state, we will be receiving the first B in its pair. Okay, because we have moved to the state Q2 when we have received the second B and we have removed the corresponding A. Okay, so now in the Q2 state, whenever we are reading a B, this will be the first B in its pair. Okay, and at the top of the push down store, suppose there is an A. So in this situation, what we have to do, because it is the first B in its pair, we don't have to remove A. Okay, so we will not remove A, we will maintain the status of the stack because we have not changed the status of the stack. So to remember that first B has come, we should change the state. Again, to what state we should go? Again, we can go to the state Q1. Why we can go to the state Q1? Because in the Q1 state, we are getting the second B in its pair. Okay, so first B in its pair, first time we have read from the state Q0, and then second and subsequent time we will read this in the state Q2. So in the Q2 state, we were getting the first B of the pair, and after getting this first B of the pair, then we will move to the state Q1. So in Q1 state, if the next B is coming, that will be the second B in its pair, and the corresponding A will be removed. Whenever again we'll move to the state Q2, and when we are in the state Q2, we are receiving a B, we are not removing the topmost symbol of PDS, that is the A. So in this manner, it will keep on moving. So by repeated use of these two transitions, we can match all the A's corresponding to the B's. So corresponding to each two B's, we are removing one A. So if my string has finished and it has exactly the twice number of B's as the number of A's, then ultimately all A's which I have pushed through these two transitions will be popped when all B's are finished. Okay. So I will be in the state Q2, and from the Q2 state, because my string has finished, I will take a null move, and at the top of the push down store there will be nothing left but the Z0. So I have to remove this Z0 and signal the success. So I will remain in the same state and I will remove this Z0 to signal the success. So this will be the solution for this A to the power n, B to the power 2n. So this is one strategy for its solution. We may have another strategy. Now we will be discussing a second strategy possible for the solution of this problem. In the previous strategy, what we have done, corresponding to each A in the input, we have pushed it over the push down store, and then during the match, corresponding to each pair of B's, we have popped one A. Means we have matched one A with every second B. Okay, so this was our strategy in the previous solution. Now what we can do, rather than exactly following the definition of the language, we can do a little bit change. Corresponding to each A in the input, what we can do, we can push two A's over the push down store. Okay, so meaning thereby, if n number of A's are present in the input, we will be pushing 2n number of A's over the push down store. And then we will do a simple matching. Corresponding to each B, we will pop one A. So means each B will be matched with an A over the push down store. So this strategy may also work. This strategy may also give you the solution. So I am writing the solution as per this strategy. So again we will start delta Q0 A Z0. This will be the initial situation. And in this situation, we will write, corresponding to the single A, we will write two A's over the push down store. So what string I have to write? I have to write double A Z0. So Z0 will maintain Z0 on the push down store, and double A means corresponding to the single A input, I have pushed two A's over the push down store. Okay. So now at the top of the push down store will be the symbol A. So the second transition will be Q0. Now I am getting another A in the input, and at the top of the push down store is A. So Q0A in this situation, I will remain in the state Q0, and corresponding to this A in the input, I will push two A's. So I will be writing here triple A. Why triple A? One A to maintain this A which was already on the top of the push down store, and two A's corresponding to this single A in the input. So that's why I will be writing triple A here. So in this manner, now again A will be on the top of the push down store. So I will keep on using this particular transition many number of times. So corresponding to each second and subsequent A, I will be pushing two A's over the push down store. So whenever I will I will be finishing all my A's, then I will be having twice the number of A's over the push down store as I have got or as I have received in the input. Now all A's has been pushed successfully. Then I will start matching. So in the Q0 state, I will be receiving first B, and A will be on the top of the push down store. Okay. So I will be doing the matching. So I will move to the state Q1 and I will write null. Is it, as we have done in previous examples as well? Okay, so corresponding to this B, that this topmost symbol A has been erased because I have changed my operation. I have moved from push to pop, so that's why I have changed the state Q1. So then delta Q1, I will be receiving another B. At the top of the push down store is A. So I will remain in this state Q1 and writing a null means I will be deleting this topmost push down store symbol, that is A. So corresponding to each B, I will be removing an A. So this particular transition, I will be using multiple number of times and I will be removing one A corresponding to each B's. And if number of B's are exactly twice the number of A's, and we have pushed twice the number of A's as we were having in the input, so number of B's should get exactly be matched with the number of A's. And when all B's will finish, all my A's from the push down store should have been popped up, should have been removed. Okay, so this will be the situation. Now I will be in the state Q1. My string, input string has been exhausted, so I will be taking a null move, and at the top of the push down store will be Z0 because all A's has been popped. So I will remain in the state Q1 and I will remove this Z0 to signal the success. Now you can see that this solution is much easier than the previous solution. So now it is up to you what strategy you take, what strategy you think. So previous solution was exactly following whatsoever given in the definition, that corresponding to each two B's we have to pop one A, and this is our innovative strategy, that rather than exactly following the definition, what we do, we are having n number of A's, but we will be pushing 2n, double number of A's over the push down store. Then we will and then we will be matching each B with each A. So in this manner we can solve this problem. So this also shows the fact that if you are writing transitions of a PDA, it is not necessary that there is a single way to write that. There may be multiple strategies, and each and every one can find its own strategy to solve the problem. If a strategy is correct, solution will also be correct. Now come on to our next example. That example is that L is a to the power n, b to the power n, such that n greater than equal to 1, union a to the power n, b to the power 2n, n greater than equal to 1. Meaning thereby, my words in this language can either be from of this format where the number of A's and number of B's are equal, or of this format where the number of B's are twice the number of A's. So any one of these two formats my words can have. So if you carefully look at the language, and as the definition of the language itself tells, that it is the union of two context-free languages. Okay, so how to write our PDA corresponding to such a situation? If we have such a situation present, or we are able to identify that our given language is the union of two different languages, then we will try to find the PDA corresponding to the each language different. Okay, so we will make a PDA corresponding to the first language, we will make another PDA corresponding to the second language, and then we will try to merge those PDAs. Okay, this is the similar strategy which we have followed when we were designing context-free grammars. So whenever we were able to find that our language is union of two different languages, then we were to write the context-free grammar corresponding to each of the language, and then we were having the method to combine those two grammars in the form of, suppose from the start symbol S1 we are deriving the first grammar, and suppose from the start symbol S2 we are deriving the second grammar. Then corresponding to their union we were adding only one production, that was S2, S1 oblique S2. So from this it was possible that from S we can move either to S1 or to S2. So if we have to generate a word from the first language, then from S we will move to the S1, and we have to generate the second word in the second language, then from S we will move to the S2. So this was the strategy. So similar strategy we will be following here. Now as you can see that I have already written the different PDAs corresponding to these two given languages. So this is the PDA corresponding to the first language, and these are the transitions of PDA corresponding to the second language. You can easily understand that through these two transitions I have pushed all the A's, and then through these two transitions I have matched each B with an A. Okay, and if matching is successful, then from through this transition I am signaling the success by removing the Z0. Here I have taken Q as the initial state and Z0 as the initial push down stored symbol. Now here we have to keep in mind that start state for both the PDAs should be different, but the push down stored symbol, initial push down stored symbol for both these state will be same. Okay, so that's why I have taken Z0 here and Z0 here, and I have taken Q here but Q dash here. So Q dash is the initial state here and Q is the initial state here. So as I have explained you, through these two I have done the pushing of all the A's, and through these two transitions I have done the matching of each A with the corresponding B. And if the matching is successful, then I am removing the Z0, making my PDS empty and signaling the success. Okay. Now here it is corresponding to the A to the power n, B to the power n. Here I have used the strategy which I have described in just in the previous example. Okay. Here corresponding to each A, I am pushing 2 A's. So if there are n number of A's, I am pushing 2n number of A's and then matching each B with each A. Okay. So here in the initial situation corresponding to this first A, I am pushing 2 A's, and then corresponding to the subsequent A's, again I am pushing 2 A's. Okay. So in this manner I am pushing double number of A's, and then through this I am doing the matching corresponding to each B. I am writing null here, so topmost symbol A is erased. So that's why matching is being done here. Now in this particular example, if you see here from Q dash on BA, I am moving to the state Q2. If I wish, I can move to state Q1 as well, which is the state here. Okay, because matching in both the processes is similar. So what I can do, I can write Q1 also here. But I will not advise that. I will always advise you that you should keep all the states of the first PDA and second PDA separate. So whatsoever states you are using in the first PDA, never use any of those states in the second PDA. Okay, it will reduce the complexity. It will reduce. It will make the analysis or the understanding of the PDA easier, because you are making both the PDAs separate. So keep their states separate so that they are not intermixed. Okay, because with the experience you can do this sharing as well. But at this point of time, I will advise you that you should not mingle with the states. You should keep the states of both the PDAs separate. This is my recommendation. Okay, if you are experienced enough and you can understand that particular analysis, that you are able to share these states, then you can optimize your design. You can reduce the number of states in your PDA. Okay, but at this point of time, correctness is more important. So I will advise that you keep your states separate. Okay, so once you have made the PDA corresponding to this and the PDA corresponding to the second language and first language, then you should write one transition which will add, like we have done here, S to S1 oblique S2. The similar kind of thing we will be doing here. So suppose I assume that my final PDA, which is accepting all the words in this language as well as in this language, is having the start state Q0, and the initial push down stored symbol is the same, the Z0, and then I will be taking a null move here. So I will be taking a null move, and what action I have to take? I will take an action where I will move to the state Q and maintaining the status of the push down stored, that is the Z0, or I will move to the state Q dash and maintaining the status of the push down stored symbol, that is the Z0. What will be the effect of this transition? Because it is a null transition, so I am not taking anything from the input, and this null transition I will always be using in the start. In the start at the state Q0, I do not have any other transition written for the state Q0 and Z0 situation. So I am bound to take this transition. Okay. Now through this transition, I am not taking anything from input, and what I am doing, suppose I want to generate a word from the first language. I will take this action QZ0. What will be the effect? I will change my state from Q0 to Q, and topmost push down stored symbol will also be maintained, that will be the Z0. So I will be in the situation when the state is Q and topmost push down stored symbol is Z0. State is Q and topmost push down stored symbol is Z0. So means this situation I will be coming, and when I will be coming in this situation, then I will be using these transitions, and using this transition means I will start functioning of this PDA. And if my word belong to the language of this PDA, ultimately I will reach to the success by emptying my push down store. Similarly, if I want to generate a word from the second PDA, I will take this second action. I will change to the state Q dash and maintain the status of the push down store symbol. Push down store, that is I will keep Z0 there. So from Q0 state, I will be moving to the state Q dash and topmost push down store symbol is Z0. So situation will be something like this. So I am in the Q dash state and topmost symbol is Z0. Then I will start functioning of this particular PDA. If my word actually belongs to this language, then I will ultimately reach to the success by emptying all the push down, by emptying my PDS when my input has finished. So in this manner, I can, this PDA can accept either the words from the first language through these transitions or the words from the second language through these transitions. So in this manner, I can write the PDA corresponding to such language, which are the union of some more languages. So corresponding to each language, strategy will be corresponding to each language. You write a separate PDA and then you combine those PDA through this null. So this will be the strategy. Now, on the basis of discussion up till today, I am giving you certain problems which I wish you solve, and we will be discussing their solution on the next lecture. And that will be our last lecture for the design of PDA. Okay. So these problems are, our first language is L is equal to A to the power 2n, B to the power n, such that n is greater than or equal to 1 means corresponding to each pair of A's, there should be 1 B's. So number of A's in our language should be exactly double of the number of B's. Okay. So then second problem is of the form, it will consist of all the words of the form A to the power I, B to the power j, C to the power k, such that j is equal to I plus k. It simply means that number of B's should be equal to the number of A's plus the number of C's. Is it? And the third language is again of the same form, A to the power I, B to the power j, C to the power k, where I, j, k is greater than or equal to 1 and I is equal to j or j is equal to k, meaning thereby either the number of A's and B's should be equal or the number of B's and number of C's should be equal. So any one of these two conditions, if satisfied, my word will be acceptable. Okay. And the last one is L is equal to A plus B asterisk A, meaning thereby all words over A and B ending with an A. So this is the language. So corresponding to these four languages, you try to make PDA at your own. In the next session, we will discuss their solutions.